So 1.2, that is comparing rates of change in linear versus, oh, why is it turned off that way? Linear versus quadratic. The idea of this section is taking data and trying to figure out whether something is linear or quadratic. But what the heck is linear anyways? What the heck is quadratic anyways? What's the difference? There's no point in me talking about this unless we know what we are dealing with. So in your own words, if someone says this is linear, what does that mean? How about I don't know if anyone told you this during an argument. If your thinking is too linear, it's more complicated than that. Anyone said that to you before? Something like those lines? No. Okay, maybe it's just me. Maria, linear? Yeah, it's linear is anything that is straight line, especially if it's slanted, aka it has a slope. Straight. Linear. And what's the contrast? What is quadratic? What if it's not linear? What does that mean? If linear means straight line, not linear means not a straight line. And what's the only not a straight line we have talked about so far? Right. How do you know, just from using this finite differences, aka these subtraction techniques, whether something is straight line or not a straight line? Some people found this so annoying that they just decided to memorize how to identify it just from looking at an equation. And that's fine too. But there are certain things that you can learn from if you know how to do the finite differences. And hint, there may be a question like this in the quiz. So at least know how to do it before you decide this is obsolete, this is underneath me, I don't need this anymore. All right? Finite differences. Finite differences are literally taking the y values when the x values are, increasing proportionally, and then subtracting them just to see something special going on. So notice that the x values are increasing by 1. The x values are continuing to increase by 1, so it is proportional. With me so far? If the x was, let's do the easy one. If the x was a 0, what's my y? 2 times 0 plus 1? 1. If x was a 1, again, what's my y? 2 times 1 plus 1. Well, 2 times 1 is 2, plus 1 is 3. Next one. If the x is a 2, 2 times 2 plus 1, go ahead, 5. Do you see a pattern? What would the next number be? Just throwing it out there. Let's move on. If x was a -1, I'll just do it very quickly. That will be 2 times -1 plus a 1. So that would be -2 plus 1. Which would be a -1. When x is a -1, my y is a -1. If x was a -2, that would be -4 plus 1 is a -3. So when x is a -2, y is a -3. I haven't done anything spectacular, really. I've just plugged in x's. Any questions about that? So if I give you an empty chart, can you do this? I hope everyone's nodding. First differences is as follows. When you're calculating finite differences, you will take all the y values and see how much I've increased. Do you remember how I wrote down the +1, +1, +1? Right? I'm going up by 1. Well, how much are the y values going up by? Well, it's easy to see right now if you just sort of count. But sometimes the numbers will be so hard, you don't know. So this is what you do. You take these two numbers, you write the bottom one first, and you subtract it because it's, differences. You subtract it with the number on top. So it would be -1 minus -3, which is -1 plus 3. The 2. Next, the bottom number is a 1. The top number is a -1. So it's +1 subtracted by -1. The same pattern. The lower number subtracted by the upper number. That's 1 plus 1. That's a 2. Next. Same pattern. The lower number subtracted by the upper number. Are you seeing a pattern? Five minus 3, 2. What do you notice about first differences? Charlie? Yeah. These, I'll use a highlighter. All the numbers that we calculated in first differences happen to be what I'm going to call constant. They're the same. They don't move. They are constant. Is that a coincidence? Maybe, but take a look. What? The first difference has the constant numbers. What can you tell me about the exponent of the x term in this equation? What exponent is here? See? What exponent is that? That's y equals 2x to the power of, yeah, it's just a 1. It's actually not a coincidence. You might not believe me. That's why I'm going to do one more example. But if the first difference is constant, then the exponent must be a 1. There is a connection between the two. And so I wrote it here. If the first difference is constant, then the degree of x, in other words, the exponent of x must be a 1. So biggest exponent must be a 1. We have no other choice. I'm going to try to prove it. Take a look at the second equation. This one's a quadratic. It's a parabola. What's the largest exponent on the x-axis? Okay. It's a 2. So just put a little note. Largest degree or largest exponent is 2. So if my pattern is correct, if my relationship is correct, then I should see the same numbers in the second difference this time. That's my guess. So let's try it. I'm going to fill this in for you. Let's see. If x equals -2, I'm going to do my calculations here. If x equals a -2, that's -2 squared minus a -2 plus 1. That would be 4 plus 2 plus 1. That is a 7. If x is a -2, my y is a 7. Let me do some mental math here. -1 squared is a 1. Minus a -1 is a plus 1. Plus 1, that would be a 3. If x is a 0, 0 squared is 0. Subtracted by 0 is 0 plus 1. fx is a 1, 1 squared is a 1, minus 1 is a, well, 1 minus 1 is 0, plus 1 is 1. And then lastly, 2 times 2, 4, minus 2, plus 1, that's a 3. Okay. Do you see a pattern with this? It looks a little funny, doesn't it? Just a little bit. Jen? Well, sort of, but careful. 7 to 3, I actually subtracted by 4, and then I subtracted by a 2, and then nothing changed, and then add a 2? What? Right? I don't know. It would be something different. Like, you know what? We can try it. So you mean a -3 or a +3? Which one do I? If this was a -3, -3 times -3 is a 9, minus a -3, so it's like a +3, that's a 12. It's actually 13. Yeah, or well, it's subtracting 6. And it's a, so let's see it out. It's really weird. So starting from here, 3 is going to be subtracted by a 7, which gives me a -4. Same pattern. The bottom number is a 1. I'm going to subtract by a 3. I get a -2. I went down by 2. Welcome. This time I have a 1. I'm subtracting by a 1. I get a 0. And then the lowest number is a 3. Subtracted by a 1, I get a 2. Is or are the first differences equal? They're not equal, right? They're not equal. So first differences are not constant. What does that tell me about the degree? Is it going to be x to the power of 1? There's no link. Not constant, not 1. First difference, not constant, not 1. So we're going to try again. Remember, our hunch is that because the largest degree is 2, the second difference should be the same. So I'm going to try it again. With the numbers from first differences, I'm going to do the lower number subtracted by the higher number. Yes, ma'am. Yeah. Name on the board. So -2 minus a -4 is -2 plus 4. That's a 2. 0 minus a -2. 0 plus 2 is a 2. And 2 minus a 0, well, 2 minus 0, that's a 2. Are they the same? Yeah. So it's not just a coincidence, I think. We've done it twice. We could do it a million times with a whole bunch of other examples, but we will find that the second differences in here are all constant. So second difference is constant. The largest degree is 2. Good morning. If the first degree is constant, the largest degree is 1. If the second degree is constant, largest degree is 2. Here's an extend. If you can see the pattern, you should be able to answer this question. What if you found that the fourth degree was constant? What would the equation look like? What could the equation look like? What do we know for sure must be in the equation? By pattern. Evita, quick pattern, okay? If it's a 1, first degree constant. I'll say it one more time. If the exponent is 1, first degree is constant. If the degree is 2, second degree is constant. Second difference is constant, sorry. If the fourth degree difference is constant, what's the exponent? Huh? 4. So this would be y equals x to the power of 4 with whatever else, but the largest degree has to be a 4. That's what we're trying to establish here. Well, I showed the math here, but I'll do it one more time. Let me share screen for just a second. Let me, sure, I can clear this. It's like this. Let me get out a stylus. I think we'll need it. And I don't need this. Very quick. So we had -2 with a 7, and you had -1 with a 3. Okay. Oh, are you asking how did I find the 7? Yeah. Then I'll backtrack. The equation was y equals x squared minus x plus 1. If the x was -2, I need to find out what y is. So I plugged it in. Every time I see an x, I plugged in a -2. Do you see how the square is here, the subtraction is here, and the +1 is still here? So every time I saw an x, I replace it with a -2. And all that's left is to solve it. -2 times -2 is a +4. Minus -2, it's like -1 times -2. This is going to be +2. Here we go. Moving on. So some examples, something that I did not do. It wrote other examples with first differences that are constant. What are differences for? It is the foundation that you need to I'm going to say this. So finite differences. It is the intro to seeing or understanding how quickly the graph changes or the y value changes. And once we see it, for example, once we see it increasing really, really, really fast, right? We apply that knowledge to other things. Like, for example, when we get to exponents and we talk about money, you'll see that it shoots up. It's just an idea of seeing how quickly the y value changes. So right now it's very basic and you don't see much use in it. But if you do progress in the world of math and you study in grade 12 and stuff like that, like there's applications for it. Okay. Some examples of when the first differences are constant. Y equals -3x minus 11, right? The exponent is a 1. Another example, y is equal to, or how about I make it a little funky? It doesn't even have to be y equals. Check this out. What if I wrote 2x minus 5y plus 10 equals a 0? That doesn't look like mx plus b. But what can you tell me about the exponent on the x? Still a 1. It's linear. I know for a fact even this is going to be a straight line because take a look at the x exponent. Yes, Charlie. Oh yeah, it's at the bottom. There too. So this was the middle one. I sort of skipped it because I was so excited to get to quadratic. So how do you know if the example is a first difference? Just make sure that your x value, the largest exponent on the x value, is a 1. It's a very straightforward relationship. I don't mean to insult your intelligence, but we have to make that connection before we move on. Next, give me an example where second differences will be constant. Somebody who's sort of catching on, but who hasn't really participated. There's only one criteria if you want the second difference to be constant, and that is so give me a random equation that fulfills this. No, I want an equation, so leave the x there. So literally, give me a number. 4. Give me another number. Give me another number. Here's one example. How do I know this one still has second differences that are constant? The largest exponent is 2. That's it. Right here. The second difference is constant. When I do the subtractions, the first difference will not have the same number. The second difference will. Yeah, that's what I mean. Yes. This equation, if I did the finite differences, if I plugged in the x's, got the y's, subtraction and subtraction, I know for a fact this one would also give me the same number every time here, the second differences. Just because I know the largest exponent is a 2. Well, that's the relationship that we're trying to prove, right? If the exponent was a 1 like this, the first differences are going to be the same. If the exponent is a 2, if the exponent is a 2, the second difference are going to be the same. Okay. And that's the end. If I gave you a question like this on a quiz with an empty chart with one equation, could you calculate first and second differences for me? I need to know that you are able to find these numbers. That's it. That's the end of your skill. That's the end of being able to communicate a relationship between the exponent and how quickly something changes. Okay, put a little asterisk on there. Just literally, if you want to try practicing from the textbooks number 1 or 4, a question like that, I'll throw it inside the quiz and away you go, right? Easy marks if you know how to do it, no marks if you don't know how to do it. It's very simple. It's not even something that you have to figure out. It's just, can you subtract? Okay, any questions? All right. In terms of conceptually, that is the last thing for today. For the remaining few minutes, I'm going to introduce a new way of writing, just like domain and range. I'm going to introduce a new way of writing equations. Turn the page. We're almost done. Yes. Yes, go quickly. I'm going to spare you the blurb. You can read it if you want to. Actually, I'll read it very quickly. In mathematics, you know, lots of questions come in context, like it tells you a story. Like for example, let's pretend that the function y equals 2000x represents how much money was made selling Gucci bags. Okay? 2000x is how much money. Mathematicians are too lazy to write all of this, right? In grade 9 and grade 10, you might have been asked to do, write down the equation, let X represent Gucci bag sold, and Y represents money. Something like that. Instead of doing it with X and Y, we can actually replace it with letters that make more sense. Like for money, doesn't it make sense to represent it with a capital M? And for the number of bags, wouldn't it make sense to replace it with the letter B? It's that idea. We write it in this funky letter and bracket method. Okay? In general, this is where our lesson starts. In general, we will replace all Y values with a new symbol, f of x, function of x. The letter f is used by default to represent a function. So here it is. Here's an example of how we would use this. Practice. Rewrite the function in function notation and then solve when the value of x is given. Let's do the first one. Y equals negative 2x minus 4. This is going to be rewritten as that. Let's get some practice. Write your fanciest f possible. Okay? Write your fanciest f and put a bracket next to it that has the letter x in it. It's followed by the equation. So the value of y is now going to be written as f of x. And I'm going to show you why this might seem more efficient. Solve when x equals -1. Mathematicians don't want to write the sentence every time. So do you know what they do instead? They do that. You see why that might be a bit more attractive for mathematicians? Instead of writing solve when x equals -1, they put the -1 where the x used to be. So what does that mean? This means plug in -1 into x. So it would be -2 times x minus 4. But no longer x, it would be -2 times -1 minus 4. That is a 2 minus 4. That is a -2. Say one more time. If x is a -1, I solve this, and I found the answer to be -2. So -2 times -1 minus 4 equals 2 minus 4 equals -2. When x was plugged in as -1, the y value that I got was -2. It's a new way of writing it. And every textbook beyond grade 10 will always be using this notation. It's a universal thing. So you're sort of making your first step into the universe of the world of mathematical scholars. Yes. The f means that whatever equation we're working with is a function. So f of x means I have a function where I need an x if I want to solve it. That's basically what it means. Or you could think of it as a function and it needs an input, like a computer. If you understand coding or you've done it before, they're always going to ask you for some kind of input and you get an output. Plug in a number and you get a number coming out. I believe the textbook makes a very, very embarrassing phrase to talk about a function. They call this function the F machine. Sounds suspicious, but imagine that you have a machine, okay, literally. Let's say you have a machine that is called F. You put something in the F machine and it spits out another number. That's literally what the textbook says, okay? Not verbatim, but it's like you put a number in there. Let's say you put a 5 in there and it will spit out a negative 11. This is the function. And I think that's a terrible way, but the textbook has it, so there it is. In the same way, if I have, let's say this is x minus 16, right? If I plugged in a 5, well, every time I see the x, I will put in a 5. What's my answer? Negative 11. You see what I mean? You put in a number and you get a number back out. This is the idea behind functions, and it's an equation. This is an equation. It's a function. It's almost always interchangeable. Yes, of course. Okay. So long story short, you plug in an x value, you will get yourself a y value. It means if x is a 5, its partner is negative 11. That is a point. In the same way here, if x was a negative 1, the y value is a negative 2. If you plug in a negative 1, you'll get a negative 2 out. That's it. Any questions? I'm going to try 2 more, but any questions after you saw it for the first time? No. Very, very silent this class. All right. A. So number 2A. Rewrite that equation as a function. I'll give you 10 seconds. 9, 8, 7, 5, 4, 2, 1. I'm hoping you rewrote it by simply replacing the y value with f of x. Now, solve when x equals 2. What does that look like? I will help you out. I want you to solve this. F of 2, the function of 2. So you're plugging in 2 into the machine. Okay, what do you get out? Give you 10 seconds. Maria? Maria, question? You got it? So in short, if x is a 2, my y value is a 4. 2, 4 exists on this graph, on this function, on this equation. Yes? That's not a bad thing. Which one? Yes. Remember, well, the question said if x is of 2. So remember, f of x is the same as saying y. They are interchangeable. So saying what's the y when x is of 2? That's what it's asking. Number 3, it would be f of x is equal to x cubed minus 2x squared plus 4x minus 10. What is the function, or what is that y value when x equals a 3? You already got it? What is it? 11? Actually, I haven't done it. 27, 9, so it's a 9, 9, 12. Yeah, right on. So everyone just check your calculations to see if it's a 11. And if you can do this, you're basically done tomorrow's lesson 2. You'll be that much more comfortable. I'm going to give you a break. If you've done copying this, you give yourself a break. we still have like 10 plus minutes. Please note, there are a couple questions you can try. These ones are word related, but I still think you can do it. And then there are 5 questions from the textbook that I think are worthwhile doing to practice finite differences as well as function notation. You make best of your time, and I will check how far you've gotten tomorrow. Bettini?